make something better, more valuable. For centuries, it's been about turning lead into gold. It's this, like, timeless fascination, this idea of elemental transformation, isn't it?
Oh, absolutely. It really taps into how we try to understand or sometimes misunderstand, what everything around us is actually made of.
Right. And that brings us right to what we're digging into today. We've got some fascinating excerpts here from Atomic Alchemy and Elemental Transformation. And it really got me thinking about this question. Could you actually just, I don't know, zap an element with light, knock an electron off, and bam, suddenly it's gold? Sounds almost, well, magical, but what's the real science? Is that even possible?
Exactly. So our mission really in this deep dive is to peel back that sort of magical layer and look at the atomic nuts and bolts. We want to get a handle on how electrons and crucially protons actually define what an element is and whether light could ever really change that definition.
Okay, let's get right to it then. Our source mentions light interacting with electrons, something called the photoelectric effect. What's the lowdown there?
Right. So the photoelectric effect, essentially, it shows us that light isn't just this smooth wave. It also acts like it's made of tiny packets of energy. We call them photons. And when one of these photons hits an atom, it can actually transfer its energy to one of the atom's electrons. Think of it like a tiny energy collision.
Gotcha. So this energy packet hits an electron. Can it actually knock it loose?
Precisely. Yeah. Each electron is held in the atom by a certain amount of energy. It's binding energy. Now, if a photon hits it with enough energy more than that binding energy boom, the electron can get kicked right out of the atom. That process is what we call ionization. The atom loses an electron, becomes an ion, and now it has an overall electrical charge.
Okay, and the source gives sodium as an example. Right,
Yeah.
Na becoming Na just by losing an electron because light hit it.
That's right, yeah. Light can definitely have enough punch to do that. And this is really the critical point, what makes sodium. It's the number of protons in its nucleus, always. Losing an electron. That just changes the atom's charge. The proton count, which is like the element's fundamental ID, stays exactly the same. A sodium ion, Na, it's still sodium. Just, missing an electron.
Ah.
So while light can strip off an electron, it's really just a surface change. It's like taking off a coat. You haven't changed who the person is underneath, fundamentally. The core identity, defined deep in that nucleus, is untouched.
Okay, yeah, that makes perfect sense. The outer layers can change, but the core building block inside doesn't. So then what does it take to actually change one element into another? To, achieve that old alchemical dream, transmutation?
Right, transmutation. That's basically the scientific term for that ancient quest. But it's not about magic. It's about a nuclear transformation. It means changing the number of protons right inside the atom's nucleus. Remember, the nucleus is the atom's core, its control center. It's got the positively charged protons, and their number defines the element, and also neutral neutrons.
Right, right. Hydrogen has 1 proton. Carbon, the basis of life, has 6. And gold, the element everyone was after, has 79 protons. A lot more.
Exactly. So if you want to turn one of those into another, you absolutely have to change that proton number. And our source talks about a few ways this can happen. One is radioactive decay. That's when unstable nuclei just sort of rearrange themselves naturally. There's alpha decay, for instance. The nucleus basically spits out a little bundle, 2 protons and 2 neutrons. That's essentially a helium nucleus.
Whoa, so if an element does that, alpha decay, it loses 2 protons. It just becomes a completely different lighter element.
Precisely. Then you've got beta decay. That one's a bit more subtle. In what's called beta minus decay, a neutron inside the nucleus can actually transform into a proton. So the atomic number goes up by 1.
A neutron becomes a proton.
Yeah. And conversely, in beta plus decay, a proton can become a neutron, which makes the atomic number go down by 1. These processes also involve spitting out other tiny particles like electrons or positrons and neutrinos.
That's just wild to think about. Inside the atom, these fundamental particles can actually switch identities.
It really is quite something. And we also see transmutation in much more dramatic events, things like nuclear fission, where a really heavy nucleus splits apart into smaller ones, or nuclear fusion, where light nuclei smash together to form heavier ones. That's what powers stars, creating elements. And of course, scientists can make it happen too through artificial nuclear reactions, basically bombarding nuclei with other particles at high speeds.
So, okay, all of these methods, decay, fission, fusion, bombardment, they all involve getting right into the heart of the atom, the nucleus, and messing with the proton count, changing the very essence of the element.
Exactly. And that brings us straight back to our earlier point. Losing or gaining electrons, which is what happens with the photoelectric effect from light, it just doesn't touch the nucleus. So it cannot transmute an element. It doesn't change the number of protons.
It's like, I guess you could say it's like changing your clothes versus changing your fundamental identity. Losing an electron is just the clothes.
That's a great analogy, actually. Yes, changing the protons is like fundamentally changing who you are. The electron change is much more superficial.
Okay, so let's nail down that original question then. Can shining light on something, knocking off an electron, turn it into gold? Based on everything we've just discussed, the answer has to be a definite no, right?
Absolutely, a firm no. Removing an electron just creates an ion. It might have a positive charge, but it's still the original element. Gold is gold because it has exactly 79 protons. Period. Losing electrons doesn't alter that number one bit. The forces holding that nucleus together are just incredibly strong. They're way beyond what, relatively gentle light interacting with outer electrons can overcome.
Huh. It's definitely less romantic than the old alchemist pictured, isn't it? A flash of light turning cheap metal into gold. That's a much nicer image than wrestling with complex nuclear physics.
Perhaps, yeah. But I'd argue the actual reality, how matter really works at that fundamental level, is even more awe-inspiring when you grasp the forces involved. Now, while light is definitely out for making gold, our source does touch on how you could potentially get gold through these nuclear processes.
Okay, here we go. This is where it gets really interesting. If just shedding an electron won't work, what could make an element end up with 79 protons?
Well, let's think about it. To end up with 79 protons, you could either start with more and lose some, or start with fewer and gain some. So consider losing a proton. If an element with 80 protons somehow lost one, yeah, it would become gold with 79. And the element with 80 protons, that's mercury, Hg.
Mercury, the liquid metal. So you're saying, theoretically, mercury could shed a proton and turn into gold.
Well, the source mentions a sort of simplified idea like UHGAO plus Pe, but in reality, a heavy nucleus like mercury just spontaneously spitting out a proton like that is pretty rare. It doesn't really happen readily. The more plausible routes involve other kinds of nuclear decay, ones that change the proton-to-neutron balance inside the nucleus, which then leads to a change in the atomic number, the proton count.
Okay, like what kind of processes are we talking about?
Well, one example that's mentioned is something called electron capture decay. This can happen with a specific isotope, mercury-197. In this case, a proton inside the mercury nucleus actually captures one of the atom's own inner electrons. That interaction effectively turns the proton into a neutron. So the proton count goes down by 1 from 80 for mercury to 79, which is gold. Another particle, a neutrino, gets emitted too.
Wow. So it doesn't spit out a proton, it sort of absorbs an electron to change a proton.
Exactly. It's an internal conversion, you could say. A subtle but really crucial difference from just ejecting a proton.
Okay. Are there other ways, like starting with fewer protons?
Yes. Another route, probably better known, it involves starting with platinum. Platinum has 78 protons. If you take a specific isotope, platinum-198, and you put it in a nuclear reactor, you can bombard it with neutrons. If it captures a neutron, it becomes platinum-199, which is unstable. Then, this unstable platinum-199 undergoes beta-minus decay, remember that one. A neutron turns into a proton, so its atomic number increases by 1, from 78 for platinum up to 79, gold. It also releases an electron and another particle, an antineutrino.
Okay, so now we're talking about nuclear reactors, neutron bombardment, unstable isotopes, decay chains. I mean, that's a whole universe away from just, like, shining a fancy flashlight on something.
Precisely. These are serious nuclear processes. They require huge amounts of energy, very specific conditions, highly specialized equipment. So, yes, scientifically, it is possible to transmute other elements, like mercury or platinum, into gold, but the sheer energy cost, the resources, the complexity, it makes it completely impractical for actually, making gold in any usable quantity. It's far more valuable as a way to understand fundamental physics than as a get-rich-quick scheme.
Yeah, no kidding. It's mind-boggling when you think about the power locked inside atomic nuclei and how that exact balance of protons and neutrons dictates literally everything about an element. That simple idea of light-changing things just seems almost quaint compared to this incredibly intricate dance happening at the nuclear level.
It really is. So just to sort of wrap up the key points from our atomic adventure today, light can knock electrons off atoms. That's the photoelectric effect. It creates ions. But this is, a surface change. It doesn't alter the element itself because the proton count is untouched.
Right. Element identity is all about the protons.
Exactly. True elemental transmutation requires changing that proton number. And that involves nuclear processes, decay, fission, fusion, bombardment.
Which means shining light on an element is never going to turn into gold.
Correct. But through specific, very energy-intensive nuclear reactions, it is technically possible to transform elements that are close to gold on the periodic table, like mercury or platinum, into actual gold. Just don't expect to get rich doing it.
Right. So the alchemists, they weren't entirely off base with the dream, but their methods, let's just say they needed quite a bit more horsepower than furnaces and potions could provide.
That's a diplomatic way to put it. They grasped the idea of fundamental change, but the change they were seeking happens at the deepest, most energetic level of matter, the nucleus.
Well, this has been a really fascinating deep dive, seriously, into the real science behind what used to be just alchemy. And it just goes to show how even questions that sound simple, like can light make gold, can lead you into these incredibly complex and frankly awe-inspiring parts of science.
Absolutely. And what's striking is that huge difference in energy scales, isn't it? The everyday interaction of light with electrons versus the colossal forces inside the nucleus. It really underscores how a seemingly small change, like losing an electron, is just fundamentally different from the profound rearrangement needed to change an element's very identity.
So as we finish up, it's clear, right, that ancient dream of alchemy, it does echo in reality, but it's a nuclear reality, not something simple like light. It really makes you think, doesn't it? About maybe other ideas we take it straightforward that might have incredibly complex, maybe surprising scientific truths hiding underneath. What else operates on a completely different level than we initially assume? Definitely something to ponder. Thanks for taking this deep dive with us today into the truly captivating world of atomic transformation.